Hi everyone. Today we're going to be talking about earthquakes and different types of faults. So the goals for today are to be able to identify and characterize different types of faults and be able to describe the type of tectonic setting that fault would naturally occur in, as well as be able to explain the elastic rebound theory and stick-slip motion on different faults which cause earthquakes, as well as then be able to explain where earthquakes are occurring and also why. So to start, what is an earthquake? An earthquake is a very rapid release of energy, and that release of energy is caused by tectonic stresses. So that release of energy causes rock to break, and the energy moves outward from the source as what we call seismic waves. So fault lines, what are faults? Faults are fractures or breaks in rocks along which displacement has taken place. So there's been displacement along a fracture or a crack in a rock. That would be called a fault. There's many different types. We're going to go over them in this lecture. So the most earthquakes are caused by sudden movement along a fault. So faults that are pre-existing are going to feel sudden motion sudden movement, I should say, that is going to cause what we know as an earthquake. Most earthquakes. So faults, I said there's many types. They are classified by the way that they move. So the relative movement from one side of the fault to the other. There's horizontal motion, there's vertical motion, or there's oblique motion, where there can be both. Horizontal motion we call strike slip. Vertical motion we call dip slip. So we're going to get into those in a little more detail. So dip slip faults, the movement is mainly vertical. So dip slip faults can either be normal or what we call reverse. Strike slip faults, the movement is mainly horizontal. So this can sometimes be called a transform fault. If you ever read about that, they're talking about a strike slip fault. So I remember this by thinking generally you strike a match by rubbing the match on the matchbox. That's generally a horizontal motion. So strike slip is going to be horizontal, whereas dip slip, when something dips, it is vertical. So that is how I remember dip slip versus strike slip. Hopefully that will help you guys too. So let's go into the differences. So a dip slip fault is where we have vertical motion. So a dip slip fault is always going to have what we call a hanging wall and a footwall. So for example, if you pictured a person standing on your fault line, so the fault line is here, diagonal. If you picture a person standing here, where would his feet be and where would he be hanging a lantern? So where his foot would be this side. So this side of the fault line is called the foot wall. This side of the fault line is called the hanging wall. So you can also think of this as which side looks like a foot. So which side has the diagonal with here we say this is the heel and here are the toes. So the toes, it's wider at the bottom than it is at the top. So the top, say, is the ankle. It's more narrow than the bottom, which is the bottom of the foot. So that is the foot wall. Now, the importance of knowing the hanging wall versus the foot wall is so that you can determine, is this a normal or a reverse fault? Is this caused by extension or compression? So, for example, here, we would say which side of this fault line, so here is the fault line. It is shown by the arrows. The arrows show you which direction the rock is moving. Which one is the foot wall? Which one is the hanging wall? So if you were standing here on this fault line, say you're standing right here, right on the fault line, your feet would be on this side. You would be hanging your lantern up here. So A would be your foot wall, B would be your hanging wall. You can also think of it as A looks more like a foot, where it's wider at the bottom than it is at the top. So A would be your foot wall, B would be your hanging wall. So this is called a normal dip-slip fault, where the hanging wall moves down relative to the foot wall. So you'll notice, you can see this brown rock layer. Here is a brown rock layer. The brown layer is on top of a yellow layer or bed. Then we have the yellow layer here. So you can see then that's on top of the green. You can see that these used to match up. Along this fault line there has been displacement. And the hanging wall has moved down relative to the foot wall. This is caused by extension. So the only way for the hanging wall to move down relative to the foot wall is if the two pieces were pulled apart slightly. So this is called a normal fault. A normal dip-slip fault is when the hanging wall moves down relative to the foot wall. So we generally find these normal faults at divergent boundaries because, as I said, you need extensional forces to be able to pull the hanging wall away or give the hanging wall room to actually slide down on the foot wall. So we generally would see these at divergent boundaries where we see extension. Divergent boundaries and normal faults, we usually see very many small earthquakes, but not many large ones. And these earthquakes are generally very shallow. That is because at our divergent boundary, we really don't have much motion with depth. So most of the motion, most of the rock motion is right at the surface. So we are not going to see very deep earthquakes. We're going to see many more shallow earthquakes. So either at a divergent boundary like a mid-ocean ridge or a rift valley, we would expect to see normal faults and very many small, shallow earthquakes. So now the opposite of a normal fault we call a reverse fault. So it's still a dip-slip fault because we have vertical motion. However, this fault line or this motion is caused by compressional forces. So what happens is if we were to, let's figure out which one is our hanging wall, which one is our foot wall. So we have A and B. Here I see that rock B, or I should say block B, looks more like a foot. It has a wider toes at the bottom, narrower at the top, like the ankle. Or if you were standing here on this, right at this fault line, standing vertically, your feet would be on block B. Your hands would be hanging your lantern on block A. So we know that A is our hanging wall, B is our foot wall. And with a reverse fault, we have the hanging wall sliding up relative to our foot wall. So you can see in these blocks that they used to be matched up. So of course these sedimentary strata, these lines here, these sedimentary rock layers were laid all at once, all at the same time. That's why they match. However, there has since been displacement. So our hanging wall has moved up relative to the foot wall. So you can imagine that if you took these two blocks and tried to push them together like these arrows show, they would slide up along that diagonal line. So the hanging wall would slide up along this diagonal reverse dip-slip fault. So compression, pushing them together, allows for the hanging wall to move up. If you were to pull them apart, the hanging wall would slide down, which would be a normal fault. So this here is our reverse fault caused by compression. So this we generally see at convergent boundaries. So here, for example, we see this fault plane. This is a reverse dip-slip fault. And here is another diagram showing the compression. So if you were to squish these two blocks together, they would slide with the hanging wall moving up along that diagonal line. Reverse faults, we can find earthquakes really at any depth, so a little different than the normal faults, because we often see reverse faults at subduction zones where we have convergence, where we have that compression. And because we know that subduction zones cause not only surface earthquakes right along that trench, but earthquakes all the way down as the subduction occurs. So we see those deep earthquakes from the subduction as well as surface earthquakes. So with reverse faults, we tend to see many different depths and strengths of earthquakes. So those are the two types of vertical motion faults. Now the other type of motion is horizontal motion. So we call these strike-slip faults. Remember, you strike a match. That's generally a horizontal motion. So you can remember that a strike-slip fault is always going to be horizontal motion. So now with our horizontal movement, there are, of course, two types. There is what we call the left lateral and the right lateral. So there's a couple different ways to remember this. I'm going to explain each of them. With the left lateral, here we have our two blocks with our fault line in the middle. And we know that this is just horizontal movement, so they're going to be sliding past each other. So when we're determining is it right lateral or left lateral, we're trying to determine which direction are they moving relative to each other. So one thing you can do is you can picture a tennis ball or a volleyball in between the two blocks. And then when you look at their motion, so here we see the block on the right moved farther away from us, farther away from the screen. The block on the left moved towards us. So we see that if we were to do that with our blocks, with a ball in the middle, the ball would rotate to the left. So then the same thing with the right lateral. If we had the opposite, where the left block is moving away, the right block is moving forwards, we would see the ball in the middle, if we were to move that block, is going to move to the right. I find this one a little hard to picture. It takes a little bit longer to sort this out when you think of this analogy. What I like to think of is which side of the fault line is moving towards you. So you, as the observer, which side of the fault line is moving towards you? So here we have the left side is moving towards me. That means it is a left lateral. Here we have the right side moving towards me. That means it is a right lateral. Now, even if we were to flip this diagram around, if you were to flip your computer screen or your phone screen upside down, it would still work. It's still the same. So the left lateral is always when the left block is moving towards you. The right lateral is when the right block is moving towards you. So here we have another example. Here we have a right lateral is this diagram here, or this diagram here, where the right side of the fault is moving towards us, towards the observer. So the third way to think about right lateral versus left lateral is to imagine you were standing on the left block here. The left block, if you were standing, say, where this arrow is, watching the motion of this side of the fault line, so watching the motion of the other side of the fault line. If you were standing here, the fault would be moving to the right. So you would see that right lateral motion. If you were standing on this side here, facing the opposite direction, so if you were standing here, facing the opposite side of the fault line, the motion would still be to your right. So you can also think of it that way. If you're standing on one side of the fault line, which direction is the other side moving? Is it moving to your right or to your left? And then a double check is put yourself on the opposite side of the fault line, make sure that it's the same, because it always should be. Otherwise, you're thinking of something backwards. So right lateral versus left lateral. My favorite way to think of it is which block is moving towards me. I usually have to do a hand motion for this and use both of my hands as the right and the left side, and then move as if there's a displacement or an earthquake. Okay, my right hand is moving towards me. That means this is a right lateral strike-slip fault. So if we look at the San Andreas, which type of fault is the San Andreas? So we know that the San Andreas is a only horizontal motion. It is a transform fault, so it's going to be a strike-slip fault. But is it right lateral or left lateral? So here we look at the two arrows showing us the motion. So if we were to picture these as the two sides of our blocks, like we have seen, so this is the two sides of the fault line being the red line there. We would see that the right, if we are looking at this as if we're standing in Mexico, for example, the right block is moving towards us. So the right side of the fault line is moving towards us. If we were standing in Washington or Oregon, we would notice, and looking towards California, that means I would have to flip my computer screen around, our right would still be moving towards us. So no matter which way you look at it, this is a right lateral strike-slip fault, the San Andreas. So here is another example. So this is a real picture after some displacement along a transform boundary or a strike-slip fault. So which direction is the fault line? So which of these would be our fault line? So we see the fence. Here's one part of the fence. Here's the other part of the fence. So they've been offset by however much distance. So that tells us that the fault line must be something similar to A. In order for this fence to be offset in this direction, the fault line must be perpendicular to the fence. So this again would be a right lateral strike-slip fault, because if we were standing right here, we would see that the right side had moved towards us. Oh, and here is the before as the straight fence. Here is the after. So here would be our fault line, So before it was a straight, nice fence. Afterwards, we had displacement of the right side of the fence moving towards us, towards the observer. So this is a right lateral strike-slip fault. And the motion is, the offset is always going to be along that fault line. So here are some examples of different types of continental earthquakes. So different types of tectonic settings that can cause earthquakes. And you'll notice that some of the dots here that show the earthquakes are deep in the earth. Some of them are just on the surface. So you'll see that the epicenter of the earthquake, we're going to learn these words in a few slides, is on the surface here. The hypocenter is down at the depth. So wherever there is an earthquake at depth, there is always a signature on the surface of the earth. So even if it is a deep earthquake, like at a subduction zone, really deep in a rift basin, or where we have some strong collision, we're always going to see the signature of that earthquake on the surface of the earth. So earthquakes and faults. These are movements that produce, faults are movements that produce earthquakes. Generally, all of the earthquakes that are produced by motion at a fault are associated with faults that already exist. So the faults are already there. And for the most part, we know about them at this point in 2020. Some faults move very, very, very slowly, so we call them creeping faults. Some faults move really big distances very suddenly. So sometimes there can be one really big change, one huge displacement, which causes a big displacement, and then there's no motion for many years. Or there are the creeping faults, which are constantly creeping. So they're moving very, 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 very slowly, but over time you can measure the offset. So about 95% of earthquakes originate in very, very narrow bands around plate boundaries. So most of our earthquakes are directly associated with plate boundaries. So here is a really cool example of a creeping fault line. So this is a curb, and here is a picture of it in 2004. So here's our curb, and the offset from this curb used to be a straight curve. So this gray was connected right up to this red. But over time, it was creeping and becoming offset. So here's a picture in 2004, and then here's the picture in 2006. So it has creeped even further. So it's creeped even this part has passed the red in just 2 years. So this was a really popular spot and a really popular field trip in this area, was to go to this famous creeping curb and measure it each year with students. It was a really popular thing until the summer of 2016 when the city repaired the curb. And it was called the Holy Grail for geologists. It was ruined. So the study of the creeping curb was ended. However, knowing that this is on a creeping fault line, we can imagine that this is just going to start over. So just because you fixed the curb doesn't mean the fault is going to stop creeping. So that creeping is going to continue, and in however many years, they're just going to have to do this all over again. So there can be both creeping fault lines, which move constantly but very, very slowly, or there can be the rapid displacement fault lines that are a little more dangerous, because with a large displacement like that, you would expect to have a much stronger earthquake. There's a lot more energy causing that bigger displacement. So when we think about the location of earthquakes, we have to think about both the focus and the epicenter. So the focus is the spot where the earthquake waves originate. So the focus can be anywhere on or in Earth. It's where the waves actually start. So the fault usually starts on the surface. The earthquake waves, the seismic waves, are going to expand outward from the focus. The focus can be on the surface, or it can be at depth. So depending on where we have, what type of motion we have, what type of fault we have, it's going to determine where we might find the focus of our earthquake. So for example, here the red dots are showing our focus. So here we have this one a little closer to the surface. Here we have a much deeper focus. The epicenter is the spot on the surface of the earth directly above the focus. So for example, here we have our focus. Here we have our focus. It's a little at depth, and then we have directly above the epicenter. Here we have the focus very deep. We have directly above the epicenter. So you'll notice that if you were on the surface of the earth, you might see that there's a fault line here. However, when you then track your earthquakes, you see that here is our fault line, but we're getting earthquakes here and way over here. That is because of this vertical and also on this diagonal motion. So our epicenters are not always right on our fault lines. They can be displaced, because that means that our focus was along that diagonal, somewhere deeper along that fault line. So that was the explanation for this question here. So here's another example. Here we have our fault scarp, which some faults will actually have a fault scarp. And what we mean by that is something on the surface showing us that a fault is there. So we might actually see evidence of your fault line on the surface of the earth. You don't always see this, but sometimes you do. When you do see a fault scarp, you know not all of your earthquake epicenters are going to be right along that fault scarp, because the type of fault that you have shows us that we could have deep earthquakes, which means that your epicenter is actually going to be offset from your fault scarp. So offset from the actual location of the fault on the surface of the earth. So our earthquakes are not always going to be right on that fault, because they can be at depth. So how do earthquakes actually happen? We call this the elastic rebound mechanism, and it can be thought of as breaking a stick. So if you think you have a not super easy to break, not a twig, but a stick you know that you can break, and you take them in both of your hands. You can hold them like this in position A, and then as you start to try and break this stick, you're building up strain. So this fault, as it is moving, as this right lateral strike slip fault, because this right side is moving towards us, as the fault is slowly moving, we're going to be building up strain on either side of that fault line. As we're building up that strain, eventually it's going to slip. Eventually we're going to crack the stick. That is what causes our earthquake. So eventually, when we get to the point where the stick is too weak, the stick is going to crack. So that buildup of strain at some point is going to be too much, and the earth is going to slip along that fault line. Where we have the weakest point along that fault is where we're going to see that slip. After that slip, the strain is released, and then the earthquake usually occurs when the rock is trying to spring back together. So you release that strain, the rock is going to then try to go back together. It's in a new position. We're going to have a lot of shaking from the slippage of that earth, of the slippage of the two pieces of earth against each other, and then the settling down into the new position along that fault. So here's just a little text description of what we just described with those images. And then here is another example. So here we see a rock wall. So a rock wall was built along this fault line. So over time, we have a right lateral strike slip fault. Oh, this is a San Andreas fault as an example. So we have our right lateral strike slip fault. That means the right side of this block is going to move towards us. So over time, the strain is going to build up. The rocks are not going to be able to slide super easily past each other. At some point, the resistance is going to be overcome, and there will be slippage, as we call it. So the blocks will slip. Where we have the weakest point along that fault line is where the slippage is going to originate from, and then the vibrations of that rock deforming is what causes the earthquake, is what causes the seismic waves that we feel as the earthquake vibrations. So a question for you all: if there was a very large earthquake right now, we are in a high probability earthquake zone, what would you do? Run outside as quickly as possible. Calmly stay upright in your seat. Run for a doorway to hide under. Get on the floor under your table or duck down in your seat and cover your head. Or Instagram Live or make a TikTok. So the correct answer would be D. Secondary correct answer might be E. If you want to get it on film, maybe you'll be on the news, maybe you'll go viral. The correct answer should be D. So what you want to do if there's a really large earthquake is you're going to want to get under the sturdiest piece of furniture that you can find. So if that's a desk, if that's a table, a coffee table, get underneath a sturdy piece of furniture and hold on to it, because the ground underneath you will be moving. What this means is a lot of injuries happen because things are falling off the walls, bookshelves are toppling over, dressers are toppling over, TVs, picture frames, things are falling off the walls. So you want to be protected by anything that could fall on top of you. So that's why they say get under a piece of sturdy furniture. So generally, a desk or a kitchen table would be the best bet for an earthquake. So you don't want to run outside. A lot of injuries actually occur during an earthquake as people are trying to move. So as people are trying to get up and run is when a lot of injuries occur because the ground isn't where you think it's going to be because it's shaking. Calmly staying upright in your seat, definitely not. You want to cover your head, so crawl down under your desk. A doorway, that's what maybe I grew up on the East Coast. This is what we were told. We never had earthquakes, so it wasn't as important. But people used to say run for a doorway, but doorways are not actually that strong. So it's shown that doorways are not the best bet, and really you want to be underneath a big piece of furniture that can try and block anything that's going to fall on top of you. So you don't want to get buried by your bookshelf or by your dresser, so get under something that will block it if it were to fall.